believe I stated in another video that nature opposes any change, delta, any change in flux. That idea is referred to as Lenz's law, and Lenz's law appears in Faraday's law as the negative sign. Lenz's law tells us the direction of polarity of the induced voltage, and therefore the direction in which currents will flow in any conductor that has an induced current. So this example is another illustration of Lenz's law, and in this case we're going to produce something known as an eddy current in a conductor. So let's get into this one. What I have is a little spatula that's sitting between, well, let me remove this. Here's our magnet, and I can illustrate. This is a magnet, again, with my paper clip. Oh yeah. Yeah. In fact, it's a pretty strong magnet. I'm going to remove the magnet for a moment and just show you that the spatula swings with nearly simple harmonic motion. There's a slight bit of damping due to the friction at the hinge. Okay. Now what happens when that conductor tries to move through a magnetic field? We get something known as motional EMF. In other words, a voltage that's induced because of the motion of the conductor through the field. Watch what happens when I let it go this time. It quickly halts when it swings through. There's a self-defeating force that appears whenever currents are induced based on Faraday's law. So think of it like this. As that spatula-shaped conductor was swinging, if this is the north pole of the magnet and then back behind is the south pole, then there would be magnetic field lines that are pointing directly away from you or into the page as I've drawn it. And I want you to consider that this piece of metal is loaded with free electrons, right? That's why it makes for a good conductor. So let's consider what happens to those free electrons that are on the leading edge of this spatula-shaped object. They'd have a velocity directed to the right as they enter this magnetic field. So why don't you try that? Use the right-hand rule. Put your thumb in the direction of the velocity of the free electrons as they enter the field, and put your fingers in the direction of the field. So there we have it. Your knuckles face downward, and so there'd be a force that would drive these electrons in the leading edge downward. But they go downward, and then they go this way, and those free electrons end up moving around in a clockwise loop. So we have clockwise drift velocity of electrons, which means we have counterclockwise conventional current. Now there's another right-hand rule you know of that helps you determine the direction of the magnetic dipole moment, or simply the direction of the magnetic field that's induced, right? This thing is moving through a magnet, but then that causes electrons to drift, and we say that means conventional current goes this way. Well, the conventional current makes this thing momentarily act like a magnet. Notice the direction of the induced magnetism. If conventional current goes this way, then that means that spatula is acting like a magnet whose magnetic field points this way, which opposes the external magnetic field. Interesting. If I let it swing this way, well, slows it down if it collides, doesn't it? Let's try to align this better so it doesn't collide. Again, without the magnet, nearly simple harmonic motion. And when it has to swing through the magnetic field, Lenz's law says there's always going to be some opposition to the induced currents. If I replace this one with this one, we still get the same effect because there's still a path for induced current. No, bad aim. One more time. Sure, it halts. Now, if this shape has to swing through, there's no broad path for current flow. You might get tiny little micro eddy currents in each tine of this fork-like shape, but that's not enough to create a significant amount of force. So I believe that this one can swing through it, same as it would nearly without the magnets. All right, Lenz's law.